Hello again, everyone. It's quite unfortunate that I cannot be present with you today, but actually, I'm quite happy to present right after great talks from Florence and Francesco, because in some sense, what I'm going to present today is some kind of result of the analysis that you can perform from the observations. And the purpose of this paper is to reconstruct for the first time with 3D distribution of the temperatures in our galaxy. So let's take a look at this map. What you see here is actually a density of the gas within 1 kiloparsec around the sun. So of course, the sun is not on scale. It's actually on the scale of a grain, if you say me, because these clouds are on the scale of 100 to 300 parsecs. So that's quite huge structures. And as you can see, as we go further from the sun, this actually is enormous. It's 1 kiloparsec around the sun. So for the first time, this map was published in Edenhofer 2024 paper. And the core idea behind the map was quite simple. You start with taking the measurements of the distances to the star from the Gaia telescope. Then you compare the photometry to assign to each star its own luminosity from the catalog. And then you compare it from the observed light that we observe. And if it differs from the catalog values for some value, then it becomes yellowish or something, that we know there is dust that absorbs the light on the way. But of course, this one measurement cannot really tell us where exactly the dust is and what's its density. It only tells us the column density on the line of sight. So, but once you take a lot of these measurements, and there are a lot, and then use some Bayesian Bayesian statistics in order to fill the gaps in the measurements, you eventually get this 3D dust map that we saw earlier. That's exactly what Edenhofer did in this paper. And this is the exact moment where our project began. Because you see, in our group, we're quite interested in interstellar medium because of two reasons. It's essential for star formation. It tells us a lot about galactic structure. So the ISM is governed by balance between heating and cooling processes. On one hand, we have heating from UV radiation and cosmic rays, which essentially affected by the distribution of UV radiation and density. On the other hand, cooling is due to quantum effects, which we call emission lines, and it's affected by the density and the temperature of the medium. So in this case, for given density and radiation field, the balance defines a thermal equilibrium state. And in SM, this balance produces multiple stable regimes, which we call cold neutral medium, is characterized by very high densities and low temperatures below 300 Kelvin. There it's this occupied the smallest volume of the ISM, but at the same time, it's quite if you're looking for the star formation, there is exactly the place where it occurs. On the other hand, we have warm neutral medium, which characterized by low densities but high temperatures, above 6,000 Kelvin. And this actually occupies the most volume of the ISM. And the last one is unstable neutral medium, which acts in classical models, acts like an interface between two stable phases, CNM and WNM. And this unstable neutral medium characterized by the temperatures between 300 and 6,000 Kelvin. So in essence, these phases correspond to different temperatures, ranges, and pressures. And that means if we know the local density and the radiation field, we can determine the thermal state of the gas and therefore its phase. So the goal of our paper was to reconstruct the 3D phase distribution of the ISM near the star. You see, modern simulations and 21 centimeter observations constrain H1 along the line of sight, but do not directly provide a full 3D density field. So we ask ourselves, could be quite interesting to see how it looks like in 3D spatial distribution. And K ingredients that we need in order to do this is, as I said, we need 3D dust map, which we already have from Edenhofer, but we also need UV radiation field, G naught. But the problem is that modern strategies to use UV radiation field is to apply it as a parameter in the system. And that's not exactly what we wanted to do for a couple of reasons. Because first of all, it misses small structures and it tends to underestimate or overestimate the WNM phase. But unfortunately, one of our authors of the paper decided to account for each individual OB star in order to, and radiatively propagate it through Edenhofer map using the luminosity was assigned by catalog values. And as an end result, Troy Porter attained the map that is going to be published in this paper, which we'll publish with the others, with our paper. And it looks like this. What you see here is, again, is IUV dust map attained from Edenhofer, propagating the Edenhofer map. Because of the issues with rendering, you can see very small sources. Also, you can see very big light structures. It's clusters. They contribute the most to the ISM, local ISM. Again, our sun is not in scale. It's actually very smaller than that. And these structures are, again, in numbers. So once we have an IUV dust map and we have 3D Edenhofer map, now we can apply thermal model in order to calculate the phases. In our paper, we used a couple of models, but as a fiducial one, we took Bialy and Sternberg model from 2019. So let's, can wait any further, let's just look at the end result. Here you see the 3D phase distribution in spatial distribution of the phases. The blue one, the blue structures, is actually a CNM called neutral medium. And these structures are numerous, as you see. They are on a scale of 100, 300 parsec. Yellowish one is unstable neutral medium, and the latter of space is filled with WNM. Again, just give you a quick opportunity to look at this beauty. So this CNM is essentially the place where star formation is occurring or will occur in the near future. And now, once we have this distribution, we may ask some physical questions. Like one, for example, is how are the ISM phases distributed vertically in the galactic disk? So here on this slide, I present you a mass fraction of each S as a function of height Z. Height is determined, 0 is the plane where the sun is at, and at each height, the curves tell us the gas mass fraction distributed between the phases. So for example, red line is WNM, yellow one UNM, and blue one is CNM. For example, if we take our plane where the sun is set, then we see that the fraction of UNM is about 48%, and CNM is 29, etc. Okay, now let's analyze this plot a bit further. As you can see, let's take a look particularly at the UNM line. What's particular about this is that modern models, classical models, expect that near the midplane, the CNM should dominate. Not only that, but UNM in classical model acts as just an interface, so it should not contribute so much mass to the total mass fraction. However, it's not what we see here. You see in the middle plane, UNM line occupies most of the ISM mass. And this surprising result kind of contradicts the standard expectation of CNM dominance and also the abundance of UNM. So let's maybe take a look at more in detail. We decided to draw PDFs of the slope that we take with a width about 60 parsec around the midplane. And okay, here I show you the probabilities distribution function of gas density and UV by phases. So black line shows all phases together, the PDF of all phases, while the red line contributes to WNM. Blue line represents CNM and yellow UNM. So what we see here on the left two plots are about density. They tell us about density, and the right one are UV. While the bottom ones are volume weighted and the top one are mass weighted. So let's first start analyzing with volume density PDF. And as we see, as expected, most of the space is occupied by WNM. Interestingly, way more UNM we get in this picture rather than what we expect from a classical models. But still, it's kind of fits our assumptions. On the other hand, of course, if you take a look on the volume-weighted IUV, we see that most of the IUV contributes from a WNM, which is quite logical because it's low-dense gas, so IUV propagates quite efficiently. And lastly, but most surprising result is that once we draw mass-weighted PDF, we see that WNM, the red curve, and CNM, the blue curve, contributes essentially the same mass to the total mass fraction, while UNM occupies most of the phase. It's quite interesting result in my sense. So the question is it physical or maybe just an artifact of the modeling or observations? So in order to address this question, we have a couple of options. First, we can try to apply the alternative thermal models. Maybe the model is a problem. So that's why we get so much UNM. Or another way to determine, to test our results is to test it on different dust map. There is one particular like et al. 2020, which was a predecessor of Edenhofer map, and it's low resolution map, so it's not really good available, but we don't really have different other maps in order to test on it, so it's quite a good opportunity to use it. So this plot essentially showed the result of this analysis. It's quite huge graph, so let's analyze it one by one. Let's go to the CNM fraction. So you see on this plot, you see CNM fraction as a function of z, which is height above the midplane. And each line represents different model or different map. So the first one is fiducial model. It's the one that we use in our paper. Essentially, we want to compare different models and different maps with this specific line. Let's first start maybe with Likey-free the dust map. It's a dashed line, and as you can see, it essentially gives the same predictions as a 3D dust map from Edenhofer. Once we go and maybe apply some different models, like Wolfire models, which have different value of ionization rate, which affects the heating rate of the interstellar medium, we see quite an interesting trend that once zeta, we start with this dashed line. This is a thin line, and it has the highest zeta value. So it's quite essentially the same as our fiducial model. Then we can go further with a smaller value of zeta, and then it goes further from the line, making CNM more dominant as zeta goes smaller. So zeta goes smaller, and CNM fraction goes higher. But let's see what's going on with UNM. Maybe we'll observe the same trend. So again, this thick dashed line is Likey-free the dust map, and we see it essentially gives almost the same prediction. It's not really diverges too much. But let's look again at the Wolfire values. So again, Wolfire goes, the highest zeta value for Wolfire is essentially gives us the same prediction as the fiducial models. But once we go smaller, for the smaller values of zeta, again, we see the same trend. UNM becomes more and more dominant, which they grow together, which meaning that the mass, they taken the mass not from each other, but rather from WNM. So it means still that taking different the different model and different dust map not really affects the results, and still we get this strange behavior of unstable neutral medium in a midplane of the galaxy. So maybe we have possible interpretations of this result. And the one that we think is contribute the most is the strong turbulence. In recent works, has been shown that turbulence really affects the UNM structure. So how does it work? In simple words, if we start with ISM, which is in equilibrium, then the classical models expect that UNM will act just like an interface between the two stable phases. And all the gas that fills in between will eventually go to one of the two stable phases. But once you add a high turbulence, then what you observe that high turbulence will kick out the stable gas from its equilibrium, and then this gas will go to the unstable medium. And of course, it wants to go back to the stable phases, but it doesn't happen because again, we have more and more turbulence in the system, and it will not allow the gas to go back to the stable regimes. And so in conclusion, what I want to say that we first of all achieved our goal, and for the first time we presented the 3D phase reconstruction of local ISM. But as a bonus, not a bonus, but surprisingly, we discovered that UNM not only dominant near the midplane, but also we discovered a way higher fraction of UNM than expected by classical models, which now suggests a highly turbulent interstellar medium. Thanks for listening, and I'm glad to hear your questions.
Thanks, Jonathan, for your talk. Is there any question here, or maybe remotely, Jérôme? No.
Thank you for this interesting talk. I had one question. So the 3D density map that you use to infer the temperature map and the distribution of the different phases has some finite resolution. So this means that the density field is somehow smoothed out. And so in the high density regions, probably the density is underestimated. How much do you think this could contribute to finding more mass in the unstable phase than in the cold neutral medium phase?
Okay. Sure enough, because this Edenhofer dust map is essentially in 2 parsec cubic resolution. So of course, we can miss some of the small structures like molecular clouds that can contribute an enormous mass to the medium. But the question is, even once we try to approximate the amount of mass that we're missing in the small structure, we come to the conclusion that even if there are some that are missing from our analysis from Edenhofer map, they will not explain entirely the amount of UNM that we get. Maybe once we apply analysis and retract this missing mass, maybe CNM will become a dominant fraction in midplane. But still, the question is, whenever UNM, why is the fraction of UNM is so high, right? Because it should be around 10% or 20% or so, but we get much more than that. And unfortunately, this small structure, in my perspective, we're still not finished with an analysis, cannot really explain the entire picture.
Okay, thank you.
Maybe another one questions, very quick.
Yes, to follow a previous question, there has been lots of studies in using the 21 centimeter emission and absorption to separate the components. So can you check along some sight line if your analysis is matching real H1 data, not this kind of thing? Because it's the same, they find this unstable phase, but not at this level. And this the H1 data just find the two components straightforward. So can you check? There must be at least 100 sidelines where you can check your model.
Mm-hmm. Well, something similar was done by one of the participants of our group, that once we get this result with high UNM fraction, we ask one of our members to check exactly that, what you on an Edenhofer map. Like we would really like to dive deep later on this topic, because it's quite different. It's quite interesting to perform comprehensive analysis with 21 centimeter measurement. But yeah, it's essentially at some point was somehow done, and we'll look at this later more comprehensively. Thank you.